So now we have all of our second derivatives, and we were doing that because we were trying to figure out what to do with Maxwell's derivation, where he combines some of his equations, or some of the equations, to make 1 over mu naught epsilon naught del cross B equals minus d2b dt2. So now we know what this is. And by the way, we did it in Cartesian coordinates, where all the unit vectors always point in the same direction no matter where you go. If we did it in spherical coordinates or cylindrical coordinates, it's much more complicated because the unit vectors change on you. If I showed you del cross vector field in spherical coordinates, you wouldn't believe me. It would scare you. You would drop the class, so I'm not going to show it to you. Okay, so this then, del cross B, we know is the gradient of the divergence B minus the vector Laplacian of B, that garbage term, and we bring this back over here. So minus mu naught epsilon naught d2b dt2. And we look at that, and look at this. This is 0. Right? There are no magnetic monopoles. Cabrera's law, that term is 0. So we're left with what ends up being the wave equation we're looking for. Del squared B, the vector Laplacian of B, which is not a real thing, mu naught epsilon naught d2b dt2. So Maxwell was playing around with his equations, and he derived what he recognized as a wave equation. When we did a wave on a string, we found that if you had an equation where you have a second spatial derivative equals a constant times a second time derivative, the solution is a wave. So this is indeed a wave equation. If we were to do this whole thing with the E field, we could. You just substitute different ones, you take a derivative of something else, and you get del squared E is mu naught epsilon naught d2e dt2. And that's also a wave equation for E. Like that. And this is why it's called Maxwell's equations. So just by modifying Ampere's law, that wasn't quite enough. He also discovered that they make waves. And when he did, he said, well, how fast do they go? Well, we know from working with waves that the velocity would be 1 over the square root of mu naught epsilon naught. And he knew that was really fast. But I believe the story is he was on vacation and he didn't have his notes with him to tell him the exact values for mu naught and epsilon naught. But he realized that's really fast, and there's one very famous wave that goes really fast, and that's light. And at the time, nobody was really thinking light was an electromagnetic wave. Right? Electricity and magnetism were being merged by Maxwell, but optics was this other thing. They weren't even sure if light was a wave at all. Maybe it was a particle. But then he realized light is an electromagnetic wave, because once you get the numbers and you plug them in, and you can do it with our numbers, it's about 3 times 10 to the 8 meters per second. So this is how you get from electromagnetism to light. And then you can go crazy and go into optics, and you can start to study what kind of equations or what kind of waves will solve those equations. And the most famous is basically an electromagnetic plane wave, which would look something like this. If it were propagating along the z-axis, it would have maybe its E field would be along here, let's see if this is, oh crud, let's see, the x cross, yeah, this is y. If it might have its E field along the x and its B field along y, and they would both vary sinusoidally in time and in phase, right? So it would come down, this would come down like that, and then this one would get smaller and go like that. And the E and B field just oscillate in and out of phase, or well, they're in phase together, in and out, traveling at the speed of light. So, and then the E field is constant over the xy plane. So that's a solution you start with, and you pretty much do all of optics from there. And it all got started when Maxwell combined his equations to find a wave equation. So a couple decades after Maxwell derived that the electromagnetic field could make a wave, people started to see it in experiments. If they made a really strong spark in one setup, they would see a disturbance in another setup far away. And they didn't do it exactly like this, but here is a rough analogy to what they did. Here we have an oscilloscope that can detect brief pulses of voltage in this wire loop. So just like we think of with Faraday's law of induction, if the magnetic field flux changes in here, we should get an EMF induced and we should measure it. So what we're going to do is spark the Wimshurst machine and see if it does anything. So you can see a nice flat signal and spark it up. So that should have triggered the scope, and you should see a nice little pulses, probably a big chaotic mess. You could say this isn't radiation. It's right there, the magnetic field. It's just essentially a DC magnetic field. So let's get farther away. So I'm going to zero this, and let's go a little bit farther out to here and spark it again. See if we still get anything. And sure enough, there it goes again. All right, let me zero it again. And I'm going to make it a little bit more sensitive. We're going to go as far as we can. So I'm going to turn it down to 200 millivolts, bring the level down to about 250, 200 or 300 millivolts, zero it out. And fortunately, we have a big lecture hall. I'll go so far away that surely we are seeing a wave. Let's see, let's go way up here. Back here where the lower end of the grade distribution sits. And this is about as far as I can get and still see you. So here we go. And sure enough, there we have sparks all the way across the room. Too far for some DC effect. This must be waves. You could take the 60 megahertz of the scope and calculate the wavelength to confirm that we really are multiple wavelengths away. But let's not do that. So there are many types of these electromagnetic waves that Maxwell discovered, and you characterize them by their wavelength. So if we were to plot one versus position, the E field, it would be a sinusoidal vibration. If we were to plot it in time, it would be moving because it's a wave. And you know that the wavelength is usually called lambda, and it's just the characteristic repeat distance of the wave. So you can characterize them with a spectrum. Basically just plot them all versus wavelength and identify them. So we can start way down here. They tend to have, a lot of them have short wavelengths, 10 to the minus 12 meters, 10 to the minus 9 meters, 10 to the minus 6 meters, 10 to the minus 3 meters, 1 meter, 1,000 meters. Electromagnetic waves have been observed at this huge range of wavelengths. And that's why they seem very different. They behave very differently. If you are way at really short wavelengths, these are gamma rays that we see from space. Very high energy, if you think of them as particles. If you're between sort of a nanometer and to here, these are X-rays. You can think of X-rays as waves, very, very short wavelength waves. In this range, up to maybe a half of a 10 to the minus 6. This is called a micron, and this is a nanometer. So up to about 400 nanometers, this is ultraviolet. And between 400 and about 700 nanometers, this is light, the light that we know, the visible light. Light that is visible. If you keep going out to up to, say, a millimeter, this is infrared, also an electromagnetic wave. If you keep going out, you get into microwaves, and you get longer and longer, and you get into radio waves. But in terms of classical electromagnetism, they're all the same. It's really just a question of scale of the wavelength. We experience them different ways. So now if we zoom in on visible light, of course the colors we see are the wavelengths. So if we were to zoom in to here, 400 nanometers is violet, and then you have blue, and way out here at 700 nanometers is red, and it's Roy G. Biv, red, orange, yellow, green, blue, violet. You've heard that before probably. But this is all the colors that we see, and I forgot that at the very intro I said I was going to explain the double sunset of Tatooine. So let me do that real quick. Okay. Double sunset of Tatooine. Finally made a mistake. So in the iconic scene, we have Tatooine, and he's there, we're yearning to be in space, and you're looking at one sun that's kind of setting, and it's very red. And the other sun is out here, and it's sort of more yellow. And you wonder, did they get it physically correct, the two colors? And of course they did, because they were both shots of the sun, right? There were no special effects that could do that in the 70s. So it's probably some double exposed shot of a real sun going from red when it's low and yellow when it's higher. To understand this, you need to know why the sky is blue and about Rayleigh scattering. So small particles and molecules scatter light, and if we were to plot how much they scatter versus their wavelength from 400 nanometers to 700 nanometers, from blue to red, it would go down very fast like that. So little particles and molecules scatter blue much more efficiently than they scatter red. Okay, so if you're sitting on your planet, and here's you, and you're looking at a sunset, you're looking at it through the atmosphere. So here's the atmosphere around your planet. And here's the sun out here. So if you look at the sun right when it's close to the horizon, it's really down here, you're looking through a lot of your atmosphere. And the atmosphere scatters out all the blue light. So the light is white when it leaves the star. We've evolved to consider it white, right? It's white when it leaves the star, and you lose a lot of the white. So the light directly that's white comes in. And if you lose a lot of the blue, you end up seeing something red. If the sun is a little bit higher, it still comes in. It's white, but it goes through less atmosphere. Less atmosphere means you lose less of the blue. You have more of the blue left. Therefore, it's less red, and it's getting more to include more of these wavelengths and including more oranges and yellows, so it looks dimmer. If you look at it right overhead, which is hard to do, it goes through the least atmosphere, and that's when it looks the whitest. So that's why the double sunset had those two different colors. Another aspect of the spectrum I can tell you about is here. This is interesting, is infrared. That's basically heat. You can have sort of heat radiation. To prove that to you, imagine you're standing near a campfire. Right? There's a campfire. I don't camp much. There's a campfire. And here's you. And it's windy outside. If you stand near a campfire, it feels really hot. Of course, that's why you light a campfire. But say the wind is blowing this way. You might think it's hot because the campfire heats the air molecules, and those air molecules heat more air molecules, and you get conduction of the heat towards you. But that's not really what it is. Mostly, it's IR radiation. Hot things emit light. Okay? So this is actually electromagnetic waves hitting you. And you know that's true because you can also go downwind of the campfire. So if you go upwind or downwind, anywhere with respect to the wind, it may help you with the smoke, but the campfire still feels hot. Okay? When you're over here, the heat is not getting blown with the wind. It's not conduction through the air. It's actual radiation that's coming and hitting you. So all these different regions of the electromagnetic spectrum we understand, and they interact with us in different ways. So now, for our final demo, I'm going to prove to you that this IR radiation is heat. So now I'm going to show you that that infrared heat that you feel at a campfire is really an electromagnetic wave. And we're going to do it by showing you that it obeys the laws of optics. So here is a parabolic mirror, and sitting at the focal point of the mirror is a very hot filament emitting quite a bit of infrared radiation. And since it's a wave, it obeys geometric optics. It bounces off the mirror surface and makes a collimated beam. So here we have a collimated beam of IR radiation. When I have my hand outside the beam, everything's fine. When I put my hand in the beam, it's very warm. So this beam of light, essentially, comes along to this mirror. So now this mirror takes all that infrared radiation and is focusing it to a point right here that's really, in principle, just as hot as the heater over there. All that heat is being focused essentially to a point. So now to prove that to you, I'm going to burn some of my notes. So I've generated a lot of notes here, kind of sick of a lot of these notes, so I'm going to find one that I really didn't like. Now here's the dream sequence. Dream sequence was a little silly, so let's sacrifice the dream sequence notes, and I'm just going to put them right in the beam, and you should see that they will ignite due to the intense heat of the IR radiation. And so I got a little red there. Give them a second. I don't know if they'll actually light or not. Let's see. Whoa, there we go. That's a lot of heat. Oh wait, I probably better copy these down. Well, anyway, let's just get rid of this. It's been fun. I've enjoyed the class. Hope you've enjoyed it. And good luck with the rest of your physics studies, and especially good luck on the final. So I'm going to show you that infrared heat you feel at a campfire is really an electromagnetic wave, and we're going to do it by showing that it obeys the laws of optics. So here's a parabolic mirror with a really hot filament right at the focus. So that's emitting the infrared radiation. And whenever you have an optical source at the focus of a parabolic mirror like this, it comes out as a collimated beam. So I have a collimated beam of infrared radiation here. And I can actually feel it. It's very hot when I put my hand here. I feel nothing when I put my hand up here because it's not in the beam. There's clearly a beam. So this beam goes to the second mirror. So this is also a parabolic mirror. It's well aligned. It's taking all that infrared radiation and focusing it to a point right in the middle. So that's a very hot place to be. Huge amount of infrared radiation being focused to a point. So to show you how hot it is, I am going to use it to light a cigarette. So this is my, now I don't want to hold my hand in there. I don't want to burn myself. So this is my steampunk opera length cigarette lighter that I made specifically for this purpose. And I'm going to hold it in there, and we'll see if it lights. Let's see, you've got to get it where it's really hot. And it usually takes a while. Okay, we're smoldering a little. And it's starting to taste terrible. When it tastes terrible, that means I'm close. Okay, so it worked. Enough heat to light the side of a cigarette. So smoking is disgusting, terrible habit. You should never do it unless it's for a physics demo, and then that's the one time it's okay. Other than that, don't ever do it. So it's been fun. I hope you enjoyed the class, and good luck on the final.